Hello, classmates. A diode is made of semiconductor material, which is a type of electronic component. Therefore, it is called a semiconductor diode. Let's begin learning about semiconductor diodes. The teaching objectives for this section are: first, to be able to describe the structure of a semiconductor diode, types, and working principles. Second, to understand the voltage current characteristics and unidirectional conductivity of diodes. First, let's look at the structure and types of diodes. The structure of a diode is very simple. A p-n junction with corresponding external leads, then encapsulated with a housing, becomes the simplest diode. Among them, the lead drawn from the P region is called the anode or positive pole. The lead drawn from the N region is called the cathode or negative pole. Its component symbol is represented by such a hollow arrow. The text symbol is VD or D. On the left side of this hollow arrow is the anode, which is the positive pole marked with a positive sign. On the right side is the cathode, which is the negative pole marked with a negative sign. The arrow here indicates the direction of the forward current when the diode is forward biased. Classification of diodes. Based on the semiconductor material used, they are divided into silicon diodes and germanium diodes. Based on structure, they can be divided into point contact types and surface contact types. The p-n junction of a point contact type is in contact in the form of a point, with a small junction area. The p-n junction of a surface contact type is in contact in the form of a surface with a large junction area. They are used in circuits for different purposes. According to their use, diodes can be divided into rectifier diodes, damping diodes, switching diodes, voltage regulator diodes, light-emitting diodes, etc. These are some pictures of the appearance of diodes. Let's take a look at what characteristics diodes have. We will also conduct an experiment to verify separately the forward characteristics and reverse characteristics of diodes. Let's connect the circuit according to the diagram. The anode of diode VD is connected to a positive 5 volts. The cathode of the diode is connected to one end of a 470 ohm resistor. The other end of the resistor is connected to the anode of the light-emitting diode. The cathode of the light-emitting diode is connected to the ground. Power on. The light-emitting diode lights up. In this circuit, the positive pole of the diode is connected to the high potential end, and the negative pole is connected to the low potential end. This connection method is called forward bias of the diode. At this time, the diode will conduct. The light-emitting diode lights up. After conduction, the voltage across the diode remains essentially unchanged. For a germanium diode, it is about 0.2 to 0.4 volt. For a silicon diode, It is 0.6 to 0.8 volt. This is called the forward conduction voltage drop of the diode. What if in the above circuit we reverse connect the diode? What will happen then? At this time, the positive pole of the diode is connected to the low potential end, and the negative pole is connected to the high potential end. This connection method is called reverse bias of the diode. At this time, in the diode, there will be a weak reverse current flowing, called leakage current. It is almost zero. The diode is in the cutoff state. If the reverse voltage across the diode increases to a certain value, the reverse current will increase dramatically. At this time, the diode is in a reverse breakdown state. If there are no appropriate current limiting measures at this time, a larger reverse current will overheat and damage the tube. General diodes are not allowed to work in the reverse breakdown state, because this will lead to the reversed conduction of the p-n junction and lose the characteristics of unidirectional conductivity. From the above experiment, we conclude that when a forward voltage is applied to the diode, it conducts. A larger forward current flows through the diode. When a reverse voltage is applied to the diode, it is cut off. The reverse current flowing through the diode is almost zero. Therefore, the diode has the characteristic of unidirectional conductivity, and it is a nonlinear component. These two graphs are the voltage current characteristic curves. For silicon diodes and germanium diodes, they reflect the relationship between the current flowing through the diode in the circuit and the voltage across the diode. Let's first look at the forward characteristics. When the diode is forward biased, there is a dead zone. When the voltage across the diode is less than this dead zone voltage, the forward current is almost zero. The dead zone voltage for a silicon diode is about 0.5 volt. The dead zone voltage for a germanium diode is about 0.1 volt. When the voltage across the diode exceeds this dead zone voltage, also known as the threshold voltage, the forward current through the diode begins to increase. When the voltage is greater than 0.6 volt, for a germanium diode, it is 0.2 volt. The forward current increases rapidly with the increase of the forward voltage. It is essentially a linear relationship. At this time, the diode is in a conductive state. After conduction, the voltage across the diode remains essentially unchanged. For a germanium diode, it is about 0.2 to 0.4 volt. For a silicon diode, it is about 0.6 to 0.8 volt. This is called the forward conduction voltage drop of the diode. When the diode is reverse biased from 0 to D, as the reverse voltage increases, the reverse current flowing through the diode is very small. It hardly increases with the increase of voltage. The diode is considered to be in a cutoff state. This current is called the reverse saturation current. We can see from the graph that the reverse current of the silicon diode is smaller than that of the germanium diode. This is also one of the reasons why silicon diodes are used more widely. After point D, the reverse voltage slightly increases. The reverse current increases dramatically. This area is called the reverse breakdown region. If there are no appropriate current limiting measures at this time, a larger reverse current will overheat and damage the tube. General diodes are not allowed to work in the reverse breakdown state. In actual engineering estimation, if the forward conduction voltage of the diode is much smaller than the external voltage, generally measured by 10 times, it can often be neglected. And the diode at this time is called an ideal diode. The characteristics of an ideal diode are: when forward biased, the forward voltage drop of the diode that is conducting can be considered zero. At this time, the diode is equivalent to a closed switch, can be considered as a short circuit between the poles. When reverse biased, the cut-off reverse current is so small that it can be considered zero. The diode is equivalent to an open switch. It can be considered as an open circuit between the poles. Let's take a look below at several main parameters of diodes. First, maximum rectifier current IFM refers to the maximum forward average current value allowed to pass through when the diode is working for a long time. Second, maximum reverse working voltage URM refers to the highest reverse voltage allowed before the diode breaks down. URM is usually half of the reverse breakdown voltage to ensure the safe operation of the diode. Third, reverse breakdown voltage UBR refers to the voltage value when the tube is reverse broken down. When broken down, the reverse current increases dramatically. The unidirectional conductivity of the diode is destroyed. It may even burn out due to overheating. Fourth, maximum reverse current IRM. The reverse leakage current when bearing the maximum reverse working voltage at URM at room temperature. It is generally very small, but greatly affected by temperature. The temperature characteristics of the diode are not favorable for the stability of the circuit. As the temperature rises, the forward voltage drop of the diode decreases. The reverse current of the diode increases with the rise in temperature. The reverse breakdown voltage of the diode decreases as the temperature rises. Well, that's it for this lesson. Goodbye, classmates.